What if everything you've ever known, every star you've gazed upon, every moment you've lived, is just a fragment of a much grander, more audacious reality? What if our entire universe, boundless and unfathomable as it seems, isn't the ultimate cosmos, but merely a seed, a singular, isolated event nestled within the infinite expanse of another, larger parent universe? This isn't science fiction. It's a frontier of physics so mind-bending, it challenges our very definition of existence. And the deepest, most profound clue to this astonishing truth might lie at the very beginning of our own story, in an event we call the Big Bang. You see, the Big Bang isn't just an origin story. It's the universe's greatest unsolved mystery, a cosmic crime scene whose true nature remains shrouded in enigma. For decades, it's been painted in broad strokes as the moment our universe came into being, a sudden eruption from nothingness. But I want you to set aside those preconceived notions, because the truth, as science is beginning to unveil, is far more subtle, far more intricate, and infinitely more profound. Imagine yourself as a cosmic detective, standing at the edge of time itself. Before you stretches a vast, expanding cosmos, our home. You can trace its history backward, through billions of years of cosmic evolution, past the formation of galaxies and stars, past the first atoms, back to a time when the universe was incredibly hot, dense, and young. You can see the echoes of this primordial fire in the cosmic microwave background radiation, a faint whisper from the dawn of time, evidence left behind like fingerprints at a scene. But as you push further, closer to that singular moment, you hit a wall, a conceptual barrier, a moment so extreme, so fundamental, that our current physics struggles to peer beyond it. This, my friend, is the Big Bang. It's not just a beginning. It's the ultimate boundary of our observable past. And like any good detective, you'd ask, what really happened here? What was this event? And perhaps most unsettlingly, what came before? For too long, the Big Bang has been depicted in popular culture as an explosive genesis, a kind of supernova writ, large, detonating in a pre-existing empty void. You probably have an image in your mind, a colossal fireball, expanding rapidly outwards, flinging matter into the darkness. It's a compelling, dramatic picture, isn't it? But it's fundamentally, beautifully, utterly wrong. And understanding why it's wrong is the first step on our journey to seeing our universe in an entirely new light. So let's dismantle that misconception right now, together. Let's have that aha moment that will reframe your entire understanding of the cosmos. Because the Big Bang was not an explosion in space. It was the expansion of space itself. Think about that for a moment. This isn't merely a semantic difference. It's a paradigm shift. If you picture a traditional explosion, you imagine a central point from which everything originates, and then debris hurtling outwards into a surrounding emptiness. But our universe doesn't work that way. When we say the universe is expanding, it doesn't mean it's expanding into something. It means the fabric of space-time itself is stretching, growing, becoming larger. Let's visualize this with a little help from our imagination and some stunning 3D animation. Forget the fiery blast. Instead, imagine an infinite, featureless surface, like the skin of a balloon that's constantly inflating. Now, picture tiny dots drawn onto that surface. These dots aren't moving across the surface. The surface underneath them is expanding, carrying them further apart. From the perspective of any single dot, every other dot seems to be moving away. And the further away a dot is, the faster it appears to recede. There is no center to this expansion, no unique point from which everything originates. Every point is the center from its own perspective. and there is no outside for it to expand into. The surface is the universe. This concept is crucial. It means that wherever you are in the universe, you would observe the same expansion. Galaxies aren't flying away from a central Big Bang point. The space between galaxies is growing, stretching, increasing the distance between them. This is why we don't see a central point of explosion in the sky. If the Big Bang were an explosion in space, we would expect to see some regions where galaxies are moving away from us slower, and others faster, depending on their position relative to the explosion's origin. But what we observe is a uniform expansion in all directions, consistent with the stretching of space itself. This incredible insight comes from Albert Einstein's theory of general relativity, a masterpiece of human thought that describes gravity not as a force, but as the curvature of space and time caused by mass and energy. When we talk about the universe expanding, we're talking about this very fabric of space-time undergoing a dynamic evolution. It's not a passive stage upon which cosmic events unfold. It is an active participant, a living, breathing entity that dictates the very geometry of our reality. So when we look back in time, we're not just rewinding a film of particles flying apart. We're observing the universe getting denser, hotter, and smaller. As the fabric of space-time itself contracts, all the matter and energy we see today were once packed into an unimaginably compact state, not at a single point in space, but as the entirety of space itself, in a state of extreme density and temperature. This reframing changes everything. If the Big Bang was the expansion of space, it means our universe didn't just appear in a pre-existing emptiness. Instead, space, time, matter, and energy all emerged and began their cosmic dance together. It eliminates the question of what was outside the Big Bang, because there was no outside. There was just it. And that it was our entire observable universe, in its nascent, highly condensed form. This profound understanding casts the Big Bang in an entirely new light. It's not a mere bang like a firecracker. It's the initial state of the universe's dynamic evolution, a moment of profound cosmic transformation. And it leaves us with an even more captivating mystery. If it wasn't an explosion in space, what was? The mechanism that initiated this incredible, accelerating expansion? What ignited this cosmic unfurling? This question, this echo, in the void of our understanding, is where the journey truly begins. Because if our universe didn't simply explode into being from nothing, then perhaps its birth was something far more intricate, far more connected. Perhaps the very event that birthed our cosmos wasn't a beginning at all, but a transformation, a metamorphosis, a cosmic event that has a striking, almost haunting resemblance to one of the most enigmatic objects in the cosmos, the black hole. What if the Big Bang, that incomprehensible moment of Genesis, wasn't an isolated event, but a profound consequence of a greater cosmic drama playing out beyond our perception? What if the universe you inhabit right now is not merely expanding, but is itself a child, born from the heart of a cosmic parent? The evidence, once you know how to look, begins to whisper this extraordinary tale. And to hear it, we must first understand the true nature of these cosmic behemoths, these devourers of light and time, known as black holes, because within their terrifying embrace, we might find the blueprint for our own existence. For decades, the very phrase black hole conjured images of cosmic vacuum cleaners, ravenous beasts, tirelessly devouring everything in their path. Perhaps you've imagined a gaping maw in the fabric of space, relentlessly sucking in stars and planets, a bottomless pit from which nothing, not even light, could ever return. And while that imagery captures a sliver of their profound mystery, it doesn't quite capture their true nature. In fact, it might lead you astray from understanding why these colossal enigmas are now central to our cosmic origin story. To truly grasp the black hole, you must first demystify it. A black hole isn't merely a thing floating in space, an object with a surface you could touch or a shape you could delineate. It is, at its heart, a profound consequence of gravity. Gravity taken to its absolute, most extreme limit. It's the universe's most dramatic illustration of how mass can warp the very stage upon which all cosmic events unfold, space-time itself. Think back to the profound insights of Albert Einstein, whose general theory of relativity revolutionized our understanding of gravity. Before Einstein, gravity was often described as a mysterious force, an invisible hand pulling objects towards each other. But Einstein showed us something far more elegant, far more interwoven with the fabric of reality. He revealed that gravity isn't a force at all, in the traditional sense. Instead, it's the bending, the curving, the warping of space-time, caused by the presence of mass and energy. Imagine space-time not as an empty void, but as a vast, invisible, incredibly supple sheet, stretched taut across the cosmos. This is our cosmic sandbox. When you place an object, say a small pebble, onto this sheet, it creates a tiny, almost imperceptible dimple. If you roll a marble nearby, it will curve its path as it passes the pebble, not because the pebble is pulling it, but because the marble is simply following the new curved geometry of the sheet. Now, imagine placing something truly massive onto that same sheet. A bowling ball, for instance. The sheet would sag significantly around it, creating a deep, pronounced indentation. Any marbles rolling past would be drawn much more dramatically towards the bowling ball, caught in its gravitational well. This, in essence, is how stars and planets exert their gravitational influence. They are massive objects that curve the space-time around them, and everything else simply follows the contours of that curvature. But what happens when you concentrate an unimaginable amount of mass into an infinitesimally small space? What happens when a dying star, many times more massive than our Sun, collapses under its own immense gravity? It doesn't just create a deeper dimple. It punches an impossibly deep well, a chasm of infinite depth through the very fabric of our cosmic sandbox. This, my friend, is where the black hole truly begins to take shape in your mind. Visualize that sheet of space-time again. As the mass becomes more and more concentrated, the well it creates gets deeper and steeper. The sides of this well become so precipitous that anything falling into it gains incredible speed. For non-celestial objects, there's still an escape velocity, a speed you could reach to climb back out of the well. For Earth, it's about 11 kilometers per second. If you launch a rocket faster than that, it escapes Earth's gravity. But for a black hole, the well is so profound, so infinitely deep, that the escape velocity required to climb out of it exceeds the fastest speed possible in the universe, the speed of light. This is the crucial mind-bending point. If nothing, not even light, can travel fast enough to escape, then the region around this extreme well becomes a one-way street. This brings us to the aha moment, the profound realization that a black hole isn't a thing in the conventional sense, a solid object with a defined surface. Instead, it is a place. It is a region of space-time, so profoundly warped by gravity that once you cross a certain boundary, there is no turning back. That boundary, that cosmic event horizon, is the point of no return. Imagine yourself as an intrepid astronaut approaching this region. You wouldn't see a gaping physical hole in space. What you would observe initially would be the surrounding stars and galaxies looking distorted, their light bent and twisted by the extreme gravity. As you got closer, the light from behind the black hole would be focused into an impossibly bright ring around the edges, forming a halo. You might see a swirling disk of superheated gas and dust, an accretion disk spiraling inwards, emitting X-rays and gamma rays as its particles rub together at relativistic speeds. This is the last gasp of matter before its inevitable plunge. But the black hole itself, the whole part, that would appear as a perfect inky black sphere, a void silhouetted against the glowing accretion disk. This isn't because something is absorbing light from that region. It's because no light from within that region can ever reach your eyes. It's not an object you're looking at, but an absence of information, an absence of light, due to the extreme curvature of space-time. As you drift closer to that event horizon, your sense of direction would begin to unravel. Within the event horizon, all paths, no matter which way you oriented your spacecraft, lead inwards, towards the singularity at the center. It's no longer just a matter of down. It's a matter of future. The forward direction in time becomes inextricably linked with the direction towards the singularity. There is no up, no sideways that leads to escape. All spatial dimensions point towards the inevitable. And what of time itself? For an observer far away, watching you approach the event horizon, something peculiar would happen. Your clocks would appear to slow down. Your movements would seem to freeze, becoming infinitely sluggish as you neared the boundary. To them, you would never quite cross the event horizon. You would simply appear to hover there, perpetually frozen in time, forever just on the cusp of the unknown. But for you, the astronaut, your clock would tick normally. You would experience the crossing of the event horizon, the moment of no return, without any special sensation. It's only once you've crossed it that the universe, as you knew it, irrevocably changes. Inside that place, the tidal forces would become immense. If you were falling feet first, the gravity pulling on your feet would be astronomically stronger than the gravity pulling on your head. This differential force would stretch you, elongating your body like spaghetti, a process chillingly known as spaghettification. You would be stretched thinner and thinner, longer and longer, until your very atoms were ripped apart. And all paths lead to the singularity, that mysterious point of infinite density, where all the mass of the black hole is crushed into a volume smaller than an atom. The laws of physics, as we currently understand them, break down there. So, when we talk about a black hole as our prime suspect in the cosmic origin story, we are not talking about a literal cosmic vacuum cleaner. We are talking about a region of space-time defined by such extreme gravity, such profound curvature, that it creates a one-way portal, a cosmic trapdoor from which nothing can emerge. It is a place where space and time become indistinguishable, where the very fabric of reality is stretched, torn, and compressed beyond all recognition. Now, hold that image in your mind. The extreme density, the overwhelming gravity, the incomprehensible curvature of space-time, the event horizon, that boundary of no return, the singularity, the ultimate collapse. Does any of this sound familiar? Does it stir any echoes of the conditions we imagine existed at the very beginning of our own universe? Consider the Big Bang. Our universe, in its infancy, was an unimaginably dense, hot, and compact state. All the matter and energy of the observable cosmos was compressed into a region smaller than an atom. The space-time within that primordial speck must have been curved to an extreme beyond our comprehension. In that initial moment, the forces at play, the densities achieved, were so immense that they beggar belief. What if the Big Bang itself wasn't an explosion into pre-existing space, but rather the creation of space and time from a point of extreme compression? What if the initial conditions of our universe bear a striking, almost identical resemblance to the conditions found within the core of a black hole? This is where the hypothesis truly begins to take root. What if the place of no return, the event horizon, isn't just a boundary around a dying star, but a cosmic birth canal? What if our entire universe, with all its galaxies, stars, and planets, emerged from an event analogous to the formation of a black hole? Not in our universe, but within a larger parent universe? Imagine our universe as a seed, a tiny, incredibly dense seed, containing the potential for everything we see around us. And this seed didn't just spontaneously appear. It sprouted. It germinated. It was formed, perhaps, within the extreme crushing environment of a cosmic parent. A parent universe so vast and ancient that the formation of one of its black holes could become the crucible for an entirely new cosmos. A child universe budding off, expanding and evolving in its own right. This isn't just fanciful speculation. The mathematics, the very equations that describe black holes, also describe the early moments of our universe. Both scenarios involve space-time stretched, compressed, and curved to an unimaginable degree. Both involve a point of infinite density, a singularity. Though we view one as a destructive endpoint and the other as a creative genesis, the profound similarities are difficult to ignore. The initial state of our universe, that hot, dense, infinitely curved moment, feels less like a simple explosion and more like a gateway. A gateway not into nothingness, but into a new reality, born from the ultimate expression of gravity in another. So, as you ponder the depths of a black hole, no longer as a cosmic monster, but as a region of space-time where gravity has utterly triumphed, consider this. What if the very walls of our cosmic sandbox were once the event horizon of another? What if the Big Bang was less of a chaotic bang and more of a quiet, inevitable unfolding from a place where space and time itself twisted into something entirely new? The journey into this idea has only just begun. We've introduced our prime suspect, the black hole, and peered into its enigmatic heart. But the true evidence, the subtle clues embedded in the very fabric of our expanding cosmos, awaits our closer inspection. How could such an extraordinary claim, this biological metaphor of a universe sprouting from a cosmic parent, possibly be supported by observation? The answers lie in the subtle yet profound ways our universe behaves, and how those behaviors echo the very nature of the ultimate gravitational well. The answers lie in the subtle yet profound ways our universe behaves, and how those behaviors echo the very nature of the ultimate gravitational wells. You see, the universe, much like a black hole, possesses a boundary, a horizon beyond which lies mystery. But these aren't just any boundaries. They are profound limits, woven into the very fabric of space-time. And their similarities are nothing short of breathtaking. Imagine for a moment standing at the edge of an abyss. For a black hole, this abyss is defined by its event horizon. We've touched upon it before, this point of no return. But let's truly step inside its implications. If you were to cross an event horizon, you wouldn't feel a thing at that precise moment. There's no wall, no force field. Yet, in that instant, your future becomes irrevocably sealed. Every path, every trajectory you could possibly take, no matter how much you ignite your engines or struggle against the current, leads inevitably inward towards the central singularity. Your future is now defined, not by choice, but by the overwhelming geometry of space-time itself. Time, for you, inside this cosmic trap, is no longer a dimension you move through, but a direction you are inexorably dragged along. It's a one-way street, and the only destination is the ultimate crushing end. Now, shift your perspective entirely. Look out into our own universe. You stand on Earth, gaze up at the night sky, and you are surrounded by stars, galaxies, and the faint afterglow of the Big Bang itself. But there's a limit to what you can see. No matter how powerful our telescopes, there's a boundary to the observable universe, a cosmic horizon. This isn't a physical wall in space. It's a limit imposed by time. Light travels at a finite speed, and our universe has a finite age. So, there are regions of the cosmos so distant that their light simply hasn't had enough time to reach us since the Big Bang. Think about it. Just as the event horizon of a black hole dictates a future you cannot escape, our cosmic horizon dictates a past you cannot observe beyond. Light from beyond that cosmic edge is forever out of reach, not because it doesn't exist, but because its journey to us would require more time than the universe has yet provided. It's a boundary of information, a limit to our knowledge of the universe's earliest moments. Here is where the true revelation begins to unfold, where the universe starts to whisper its deepest secrets. Look closely at these two horizons, the black hole's event horizon and our universe's cosmic horizon. They might seem like opposites, one pointing to an inescapable future, the other to an unobservable past. But mathematically, geometrically, they are mirror images of each other. Imagine you are in a vast mirrored hallway, stretching infinitely in both directions. On one side, you see the reflection of a black hole's interior, its event horizon defining a boundary that funnels everything forward in time towards a future singularity. On the other side, you see the reflection of our own universe, its cosmic horizon defining a boundary that points back in time to an unobservable past, the Big Bang singularity. Inside a black hole, everything, every particle, every ray of light, you yourself, if you were to fall in, moves inexorably towards a single point in the future, the singularity. It's a collapsing, a converging journey. The very paths of space and time bend inward, ensuring all trajectories end at that central future point. Now, consider our universe. From our vantage point, everything we observe, distant galaxies, cosmic background radiation, appears to be moving away from a single point in the past, the Big Bang. It's an expanding, diverging journey. The very fabric of space is stretching, pushing everything apart, as if originating from a central past point. Do you see the profound symmetry? The geometry is precisely the same, only the arrow of time is reversed. Inside a black hole, space is contracting towards a future singularity, while in our universe, space is expanding away from a past singularity. The mathematical equations that describe the space-time within a black hole's event horizon are stunningly similar to the equations that describe the space-time of our expanding universe, with one crucial difference. The role of time and space are swapped. For an observer falling into a black hole, the direction inward towards the singularity becomes indistinguishable from the direction forward in time. There is no longer a way to move backward in time or outward in space once past the horizon. Similarly, for us in the expanding universe, looking back in time towards the Big Bang is like looking towards a specific point in the past, a singularity from which all paths diverge. This isn't just a quirky coincidence. It's a deep, structural correspondence. The aha moment arrives when you realize that the Big Bang, which we typically envision as an explosion in space, might be better understood as an event of space-time, a boundary in time, and the singularity within a black hole is also a boundary in time, just in the future. The expansion of our universe, the way galaxies recede from us, the way the cosmic microwave background radiation is stretched and cooled. All these phenomena, when described by Einstein's general relativity, bear an uncanny resemblance to the physics of collapse inside a black hole. It's as if our universe is playing out the script of a black hole's interior, but with the film running backward. Think of the Big Bang as a white hole, a theoretical time-reversed black hole, where nothing can enter and everything is spewed out. While white holes are often considered mere mathematical curiosities, this mirrored geometry suggests that perhaps our universe's origin is not a white hole in the traditional sense, but rather the interior of a black hole in a parent universe, where the outward explosion we perceive as the Big Bang is simply the natural expansion of space within that unique gravitational environment. The cosmic seed, blooming from its parent, this mathematical mirroring, implies that the singularity of the Big Bang, that infinitely dense point from which everything supposedly emerged, might not be a point in space, but rather a moment in time that is mathematically equivalent to the singularity at the heart of a black hole. It's not a location we can point to in the sky, but a boundary of our past, just as the black hole's singularity is a boundary of its future. This profound equivalence, this tale of two horizons, suggests that the very geometry that governs the ultimate fate of matter within a black hole might also govern the ultimate origin of our entire cosmos. It gives us a framework, a mathematical bridge, to connect the seemingly disparate realms of the infinitely small and the infinitely large. It transforms the abstract idea of a universe born from a black hole into a tangible, geometrically consistent possibility. It invites you to reconsider the nature of reality itself. What if the grand narrative of our existence, from the first flicker of light to the farthest reaches of observable space, is simply a chapter in the life cycle of a much larger, unseen cosmic entity? What if the universe you inhabit is merely an echo, a reflection, a child of a profound gravitational embrace? This profound equivalence, this tale of two horizons, suggests that the very geometry that governs the ultimate fate of matter within a black hole might also govern the ultimate origin of our entire cosmos. It gives us a framework, a mathematical bridge, to connect the seemingly disparate realms of the infinitely small and the infinitely large. It transforms the abstract idea of a universe born from a black hole into a tangible, geometrically consistent possibility. It invites you to reconsider the nature of reality itself. What if the grand narrative of our existence, from the first flicker of light to the farthest reaches of observable space, is simply a chapter in the life cycle of a much larger, unseen cosmic entity? What if the universe you inhabit is merely an echo, a reflection, a child of a profound gravitational embrace? This tantalizing question, this whisper of cosmic parentage, leads us directly to the heart of one of the deepest mysteries in all of physics. What actually happens at the very center of a black hole? And by extension, what truly happened at the moment of our universe's birth, the Big Bang? For decades, our most powerful theory of gravity, Einstein's general relativity, has painted a stark, almost terrifying picture for both scenarios. It predicts something called a singularity. Imagine, if you can, a point of infinite density, infinite curvature, where all the laws of physics that you and I understand simply break down. Our equations, our elegant mathematical descriptions of the cosmos, cease to function. They hit a wall, an insurmountable barrier beyond which we cannot see, cannot predict, cannot even begin to comprehend. At the heart of a black hole, this means all the matter that crosses the event horizon is crushed inexorably into an infinitely small point. For the Big Bang, it means our entire universe, with its billions of galaxies and countless stars, emerged from an infinitely small, infinitely dense point. An infinity in science is often a red flag, a signal that our current understanding is incomplete, that there's a deeper layer of reality waiting to be uncovered. Nature, in its elegant wisdom, rarely deals in true infinities in its fundamental operations. There is almost always a finite, albeit extreme, boundary. This conceptual abyss, this breakdown of understanding, has long been a source of profound dissatisfaction for physicists. It's like reaching the edge of a map and seeing "here be dragons" instead of new lands. But what if this isn't an end point at all? What if the singularity isn't a dead end, but a turning point? What if, instead of being crushed into infinite nothingness, matter reaches an incredibly dense but fluid state, and then bounces back? This is the essence of the Big Bounce hypothesis. It's a radical departure from the traditional Big Bang, suggesting that our universe didn't begin from an infinitely dense point, but rather from the collapse of a previous universe, which then rebounded. Picture it as a cosmic inhale and exhale. The universe contracts, reaches a maximum yet finite density, and then, driven by fundamental forces, begins to expand again, giving birth to a new cosmos. It replaces the infinite singularity with a moment of extreme, but ultimately manageable compression. Now let's bring this abstract idea down to earth, or rather, to a more intuitive scale. I want you to visualize something truly remarkable with me. Think of a tiny seed. It might seem small, unassuming, even inert, but within its seemingly simple structure lies the complete genetic blueprint for an entire tree, an entire forest, an entire ecosystem. This seed, however, needs specific conditions to sprout: water, warmth, and crucially, pressure. The soil compacts around it, holding it in place, providing the necessary resistance for the internal forces of life to push outwards. In this context, the incredible gravitational pressure at the heart of what we call a singularity isn't a destroyer, but a catalyst. It's not crushing matter to oblivion. It's preparing it, compacting it, for a monumental act of rebirth. Our universe, then, could be like a cosmic seed, germinating from the extreme conditions of a parent cosmos. This cosmic seed metaphor suggests that the boundary we once thought of as an absolute end, the singularity, is in fact the ultimate beginning for a new realm of existence. But what could possibly provide the force to prevent infinite collapse and drive such an extraordinary bounce? This is where we must venture beyond classical general relativity and into the realm of quantum gravity, a field still under active development, but one that offers tantalizing glimpses into the true nature of reality at its most extreme. One promising avenue, one that aligns exquisitely with the idea of a universe born from a black hole, lies in an extension of Einstein's theory known as the Einstein-Cartan theory. While general relativity describes space-time as being curved by mass and energy, the Einstein-Cartan theory introduces an additional geometric property: torsion. To understand torsion, you need to think about the fundamental properties of matter itself. Elementary particles, the building blocks of everything you see, feel, and are, aren't just tiny, featureless points. They possess an intrinsic angular momentum, a fundamental spin. Imagine them as minuscule, perpetually rotating tops. In the Einstein-Cartan framework, this inherent spin of matter doesn't just exist in isolation. It actually twists or torques spacetime itself. Now, here's the aha moment, the profound insight that could solve the singularity problem and give birth to new universes. At the relatively low densities we experience in our everyday lives, or even within stars, the effects of this space-time torsion, due to quantum spin, are incredibly subtle, almost imperceptible. But as matter is compressed to the unimaginable densities found at the heart of a black hole, or at the moment of maximum compression, preceding the big bounce, something extraordinary happens. The collective effect of all these tiny quantum spins, twisting space-time, becomes incredibly powerful. So powerful, in fact, that it generates a repulsive gravitational force. Yes, you heard that correctly. A repulsive gravitational force. Instead of gravity always pulling inward, endlessly crushing everything, at these extreme, quantum-dominated scales, it can actually push outward. Think of it like this. Imagine trying to compress a spring beyond its natural limits. The more you push, the stronger its resistance, until it eventually pushes back with immense force. Quantum spin, woven into the fabric of space-time through torsion, acts like this cosmic spring. As matter reaches the point of ultimate compression, this quantum repulsion kicks in, overpowering the attractive force of classical gravity. It acts as a fundamental barrier, preventing matter from collapsing to an infinite point. It halts the collapse at a finite, albeit incredibly dense, state. And then, this powerful repulsive force doesn't just stop the collapse, it drives the expansion. It bounces the universe back out. It's the ultimate cosmic recoil, an intrinsic property of space-time and quantum matter, preventing self-destruction, and instead, instigating creation. So, a black hole's singularity, far from being a dead end, transforms into a dynamic cosmic crucible. It's a place where quantum spin acts as the germinating force, where the immense gravitational pressure, instead of destroying everything, activates this fundamental quantum repulsion. It's a profound reimagining of one of the universe's most enigmatic phenomena. Our Big Bang, then, wasn't an explosion from nothing, but a big bounce from something. The supercompressed, quantum spin-driven interior of a black hole in a parent universe. You are, in essence, living inside a universe that sprouted from a cosmic seed, watered by the immense gravity of another, larger cosmos. This isn't just a theoretical curiosity. It offers an elegant solution to the singularity problem that has plagued cosmology for so long. It suggests that the universe is not a one-time event, but part of an ongoing, possibly infinite, process of creation and transformation. It means that within the heart of every black hole, there might be not an end, but a new beginning, a new cosmic seed, patiently awaiting its moment to sprout. Imagine the implications for your own existence. If our universe is a child of another, then perhaps we are part of an endless lineage of cosmos, each giving birth to the next, in a magnificent, self-sustaining cycle. It means that the universe is not just expanding into empty space, but perhaps expanding out of a highly compressed, quantum-fueled state within a larger gravitational structure. The boundaries of our universe become permeable, connected to a vast, unseen network of cosmic parentage. What if the very fabric of existence is woven with these threads of interconnectedness, where the end of one cycle is always the beginning of another? If this grand tapestry of cosmic parentage is real, wouldn't it leave a signature? Wouldn't there be indelible marks, like a cosmic fingerprint, hinting at its true nature? Sometimes, the most profound revelations don't come from sweeping pronouncements or grand theories alone, but from the quiet, insistent whisper of numbers. They are the universe's own language, spoken in ratios, in constants, in measurements that, when truly observed, can shatter our preconceived notions of reality. For decades, cosmology has grappled with the vastness and peculiar characteristics of our universe, charting its expansion, measuring its contents, and attempting to piece together its genesis. But what if, hidden within the very data we've collected, there lies an astonishing pattern, a numerical echo that points directly to the black hole hypothesis? Through these painstaking observations, they estimate the total mass energy contained within our observable universe. This isn't just about the stars and planets you can see. It includes the vast, invisible seas of dark matter that gravitationally bind galaxies together, and the enigmatic dark energy that drives its accelerated expansion. Now let's take a conceptual leap back to Albert Einstein's field equations, the very bedrock of general relativity that describes gravity not as a force, but as the curvature of space-time. These revolutionary equations led to one of the most mind-bending predictions in all of physics, the existence of black holes. Crucially, they also gave us the concept of the Schwarzschild radius, a theoretical boundary around any mass, the ultimate point of no return. And here's where the cosmic fingerprint begins to emerge with startling clarity. What if you were to take the estimated total mass energy of our entire observable universe? Every galaxy, every particle, every quantum fluctuation, every ounce of dark matter and dark energy, and hypothetically compress it into a single gargantuan black hole. You can calculate this. It's a straightforward, albeit mind-bending calculation based on the established laws of physics, a theoretical exercise in extreme gravity. And when you perform this calculation, a number appears, a staggering, immense number, representing the theoretical boundary of a black hole. Now, hold that number in your mind, because there's another number, an independently derived measurement that defines the boundary of our actual, observable universe. This is the cosmological horizon, the limit of how far light has had time to travel to us since the Big Bang. And here is the first breathtaking match in the cosmic fingerprint. The calculated Schwarzschild radius for a black hole with the mass of our entire universe turns out to be almost identical, astonishingly close, to the measured radius of our observable universe. Think about the sheer improbability of that. On one hand, you have a purely theoretical calculation based on the mass of everything we know, imagining it compressed into a black hole. On the other, you have a direct observational measurement of the boundary of our actual universe, determined by the speed of light and cosmic time. These two numbers, derived from entirely different approaches, one purely theoretical and the other empirical, align with a precision that defies mere coincidence. This isn't just a curious anomaly. It's a profound echo. It suggests that the boundary of our observable universe, the very edge of what we can perceive, might not be an arbitrary limit imposed by the speed of light and time, but rather a fundamental boundary, eerily similar to an event horizon. But the cosmic fingerprint doesn't stop there. There's another layer to this astonishing match, another numerical resonance that deepens the mystery and strengthens the hypothesis. This involves density. For our universe, we can calculate its average density by taking the total estimated mass energy within our observable volume and dividing it by that volume. Our current measurements, especially from the cosmic microwave background radiation, point to a universe that is incredibly close to a flat geometry, which means its average density is very near a specific critical density value. Now, let's return to our theoretical black hole. If you calculate the average density of such a black hole, you get another remarkable number. And here is where the second part of the cosmic fingerprint clicks into place. The calculated average density of a black hole with the mass of our universe is almost perfectly identical to the measured average density of our observable universe. These twin numerical alignments, the astonishing congruence of size, and the precise match in average density are not easily dismissed. They are compelling pieces of evidence that demand a deeper explanation. They suggest that the universe we inhabit, with all its galaxies and stars, and the very ground you stand on, operates under conditions that are mathematically indistinguishable from the interior of a colossal black hole. It transforms the concept of a black hole from a mere destroyer of matter into a potential womb of new universes. If our universe is indeed a black hole, nested within another, then the very concept of beginning and end takes on a cyclical, interconnected meaning. The universe isn't just big, it's deep. And these numerical congruences are the first tangible hints of that profound depth, the echoes of a truth that extends far beyond our current understanding. They are the data points that begin to fill in the incredible, impossible picture we started to paint. A universe born from a black hole. But if these numbers point to such an extraordinary conclusion, how do we reconcile this with what we thought we knew about the Big Bang? What mechanisms could truly bridge the gap between a collapsing star and an expanding cosmos? The journey continues, pushing us to explore the very edges of theoretical physics and the limits of our imagination. The idea that our cosmos could be the offspring of a black hole in an older, vaster universe is, by itself, a profound shift in perspective. It challenges our most fundamental assumptions about creation and the very fabric of reality. But what if that extraordinary proposition is not the end of the story, but merely the first whisper of an infinitely grander narrative? What if the mechanisms we've begun to uncover, the bridge between collapse and expansion, are not unique to our universe, but are part of a ceaseless universal process? Imagine for a moment that our universe isn't just an isolated event, a solitary bloom in the cosmic void. What if it's a single leaf on an unimaginable branch, part of an infinite, ever-growing cosmic forest? This isn't just about multiple universes existing side by side, disconnected and distinct. This is about universes that create other universes, a cycle of cosmic birth and propagation, where each black hole isn't merely an endpoint of stellar evolution, but a potential gateway, a cosmic womb, giving rise to a new universe with its own unique set of fundamental laws. For decades, physicists have grappled with one of the most perplexing mysteries, the fine-tuning problem. You see, the fundamental constants of our universe, the precise values that dictate everything from the strength of gravity to the mass of an electron, from the charge of a proton to the exact energy density of the vacuum, seem almost impossibly perfect for the emergence of complexity, for stars, for planets, for life itself. It's as if someone dialed the cosmic knobs to precisely the right settings, hitting a bullseye on a target spanning quadrillions of possibilities. Consider gravity, for instance. If it were even slightly stronger, stars would burn out too quickly, collapsing in on themselves before they could forge the heavier elements essential for planets and life. If it were slightly weaker, matter would never coalesce into stars and galaxies in the first place, leaving behind a diffuse, featureless cosmic soup. Or take the strong nuclear force, which binds protons and neutrons together in atomic nuclei. A tiny change, and either no complex atoms would form, or all hydrogen would have been converted into helium in the Big Bang, leaving no fuel for long-lived stars and no water for life. The cosmological constant, representing the energy density of empty space, is even more bewilderingly precise. It's so small that if it were just a little larger, the universe would have expanded too rapidly for galaxies to form. If slightly smaller, it would have collapsed back in on itself long ago. These aren't just minor adjustments. They are values that, if perturbed by even a hair's breadth in many cases, would lead to a universe utterly devoid of structure, of stars, of planets, of you. It's a staggering coincidence, one that has led some to propose the idea of an intelligent designer, while others suggest the existence of a vast multiverse, where our universe is simply one of countless variations, and we just happen to find ourselves in the one where life is possible. But what if there's a different, equally profound explanation. What if this isn't about design, nor is it merely a statistical fluke in an indifferent collection of parallel worlds? What if this is about evolution? This is where the theory of cosmological natural selection, proposed by physicist Lee Smolin, enters our cosmic forest. If universes reproduce through the formation of black holes, then those universes that are better at forming black holes would naturally produce more offspring universes. It's a cosmic twist on Darwinian principles. A universe's ability to propagate itself, to create new universes, becomes its measure of fitness. Think of it this way. In this immense, self-propagating cosmic forest, each new universe is like a tree sprouting from a seed. In this case, a black hole. When a new universe is born this way, its fundamental constants might not be exact replicas of its parent universe. Instead, they could undergo tiny random mutations, infinitesimally small variations in values like the strength of gravity or the mass of particles. Most of these mutations would be detrimental, leading to boring universes that fail to produce many stars, and thus few black holes, effectively ending that particular lineage. But occasionally, a mutation would result in a universe even more efficient at black hole production. This universe would then produce more offspring, passing on its slightly altered, more successful genetic code of physical laws over countless generations of universes. A process analogous to biological evolution plays out on a cosmic scale. Universes with laws that foster abundant star formation and subsequent black hole collapse would flourish and multiply, becoming more prevalent in the cosmic forest. Universes with laws that hinder this process, perhaps forming only diffuse, empty expanses or collapsing too quickly, would produce fewer offspring or none at all, eventually fading into cosmic obscurity. Our universe then, with its abundance of stars, galaxies, and black holes, wouldn't be a lucky accident. It would be a highly successful specimen, exquisitely adapted for cosmic reproduction. This means that the very fabric of reality, the rules that govern existence, are not static or arbitrary. They are dynamic, subject to a grand cosmic selection process. The laws of physics, from this perspective, are not merely given. They have evolved. And the fine-tuning that perplexed us, the seemingly miraculous precision of our universe's constants, suddenly takes on a new, profound meaning. It's not a coincidence, but the signature of a universe that has been incredibly successful at propagating itself through this black hole-driven cycle of birth. Consider your own existence within this framework. The elements that make up your body, the carbon, the oxygen, the iron, were forged in the hearts of stars. And those stars are the very engines of black hole creation. You are, in a profound sense, made of the stuff that fuels the universe's reproductive cycle. Your existence, the existence of all life, becomes an echo of a deeper cosmic imperative. The propagation of universes, the intricate complexity of life itself, requiring such a delicate balance of physical laws, might simply be a byproduct of a universe that is exceptionally good at making stars, which, in turn, are exceptionally good at making black holes. This theory offers a radical reinterpretation of the Big Bang itself. It ceases to be a singular, inexplicable beginning, but rather a continuous process of birth, an ongoing cascade of new realities emerging from the hearts of collapsing old ones. Our Big Bang, from this perspective, was merely one such birth, a specific event in an infinitely larger, endlessly unfolding cosmic drama, and the parent universe from which ours sprang would have itself been born from a black hole in its parent, stretching back into an unimaginable chain of cosmic lineage. The implications ripple outward, transforming our understanding of everything. If physical laws can evolve, What does that mean for the fundamental nature of existence? Are there universes where light travels at a different speed, where time flows backward, or where gravity repels instead of attracts? The cosmic forest suggests an infinite diversity of realities, each with its own unique genetic code of physical laws, all striving for reproductive success. And our universe is just one flourishing branch in that boundless, evolving tapestry. This isn't just a philosophical musing. It's a hypothesis that, in principle, offers testable predictions. For instance, if our universe is a product of this evolutionary process, then its fundamental constants should be optimized for black hole formation. This implies that small changes in these constants should, on average, lead to fewer black holes. Physicists are actively exploring ways to test this, seeking subtle variations or patterns in the constants that might hint at their evolutionary history. The very concept invites you to expand your mind beyond the confines of our observable cosmos. It asks you to consider that the laws you experience every day, the predictable dance of planets, the reliable glow of the sun, the very chemistry of your being, are not immutable, unchangeable truths, but rather the highly successful adaptations of a universe that has learned, through countless cycles of birth and death, how to best perpetuate itself. So, if our universe is merely one tree in an endless cosmic forest, and its laws have evolved to favor its own reproduction, what does that say about the ultimate purpose or direction of this grand cosmic evolution? This cosmic journey has led you to a truly astonishing hypothesis that our universe, with all its galaxies, stars, and life, might have sprung from the heart of a black hole in a much larger parent cosmos. The very laws and constants you perceive, the fabric of existence you inhabit, could be the refined, optimized adaptations of a universe designed to reproduce itself. It's a vision of reality as a vast, interconnected, almost biological system, constantly giving birth to new iterations. But now, it's time to shift our gaze. We've been looking outward, imagining the grand cosmic tree, the infinite forest. Now let's turn inward, to our own existence within this astounding framework. What does it mean for us here, now, if our universe is literally contained within another? Imagine for a moment that you are born into a room with no windows. You have never seen the outside. Your entire reality is defined by the four walls, the ceiling, the floor, the objects within it. You can study the texture of the paint, the way light reflects off the surfaces, the sounds that echo within its confines. You can deduce, through careful observation, that the room has a certain structure, that gravity pulls you toward the floor, that objects fall at a predictable rate. You can even, through meticulous scientific inquiry, develop sophisticated theories about how your room came to be. Perhaps you find subtle clues in the materials, hints of a construction process, an architect's hand, or even the remnants of a larger structure from which your room was carved. You might hypothesize, based on the physics of your internal reality, that this room is just one small part of a much grander building. You could even develop compelling mathematical models that describe the exterior, predicting its shape and scale, the forces that govern its construction, even the nature of the outside world. You might theorize about other rooms, other hallways, perhaps even an entire city, or a boundless landscape beyond your immediate perception. But here's the crucial point. You can never see it. You can never directly observe the outside. Your light cannot escape the room to illuminate what lies beyond its walls. Your instruments, however advanced, are bound by the very physics of your enclosed space. The walls of your room are, in a very real sense, an event horizon. They define the boundary of your observable reality. This is, in essence, our predicament if the black hole universe hypothesis holds true. We are inside that room. Our universe, born from the gravitational collapse of a parent star, is self-contained. The edge of our observable universe, the cosmic horizon, isn't just a limit to our technology. It's a fundamental barrier, much like the event horizon of a black hole. Information, light, matter. Nothing can escape our universe's boundary to reach the parent cosmos, just as nothing can cross a black hole's event horizon from the inside out and still be observed. And crucially, nothing from the parent universe can enter our universe and still be perceived as external. Any influence from the parent universe would, by necessity, be absorbed into the very fabric of our reality, manifesting as phenomena we currently struggle to explain. Consider this. Our universe is expanding. We observe galaxies rushing away from each other, a stretching of space-time itself. This expansion is accelerating, driven by what we call dark energy, a mysterious force that seems to infuse empty space. We also know that the vast majority of matter in our universe isn't the ordinary stuff we see. It's dark matter, an invisible substance whose gravitational pull shapes galaxies, but which we cannot directly detect. What if these enigmatic phenomena, dark energy and dark matter, are not intrinsic properties of our universe in isolation, but rather the subtle internalized echoes of the parent cosmos? What if the expansion we observe is the continued inflation of our universe within its parent, and dark energy is a consequence of the pressures or properties of that exterior? What if dark matter is a relic, a subtle imprint, or even a form of matter from the parent universe that has been drawn into our own, but which interacts with our local physics in ways we don't yet fully comprehend? If our universe is a black hole, its physical properties are inextricably linked to its origin. The very curvature of space-time we experience, the strength of gravity, the speed of light, all of these fundamental constants could be reflections of the conditions within the parent universe from which we emerged. This isn't to say that our reality isn't real or that our science is flawed. Quite the opposite. It suggests that our science, our physics, is incredibly robust within the confines of our cosmic room. We are mastering the internal mechanics, but it invites a profound philosophical leap. If our universe is physically contained within another, what other fundamental aspects of our reality might be different than they appear? What if the very nature of space, time, and even matter is more nuanced, more layered than our direct perceptions allow? This brings us to one of the most mind-bending, yet compelling ideas in modern physics, the holographic principle. Imagine a hologram. You look at a two-dimensional plate, yet it projects a three-dimensional image. The entire depth and detail of that 3D image are encoded on a flat 2D surface. This isn't just a fanciful notion. It emerged from the study of black holes, the very objects at the heart of our hypothesis. Physicists like Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of disorder or information. Surprisingly, this entropy isn't proportional to the black hole's volume, as you might expect for a 3D object. Instead, it's proportional to its surface area. This was a radical departure from classical physics, suggesting that all the information about what falls into a black hole isn't lost within its interior, but rather imprinted or stored on its two-dimensional event horizon. The boundary holds the key to the interior. If our universe is indeed a black hole within another, then the holographic principle isn't just a theoretical curiosity. It could be a fundamental description of our reality. The vast, expanding cosmos we perceive, the intricate dance of particles, the intricate tapestry of life, all of it could be an emergent property, a grand projection from information encoded on a cosmic boundary. that is forever beyond our direct grasp. Think about what this implies for the very nature of stuff. We perceive particles, fields, forces, all existing in three spatial dimensions. But if reality is holographic, these 3D entities are effectively pixels in a grander, more fundamental 2D canvas. It's like the difference between seeing a character in a video game and understanding the underlying code that generates that character. The character is real within the game's context, but its ultimate reality is a string of data. This doesn't mean you are a simulation in the way a computer program runs on a chip. It's far more profound. It suggests that the fundamental degrees of freedoms of our universe, the most basic bits of information that make up reality, reside on a lower dimensional surface, and what we experience as 3D space is a complex emergent phenomenon. Our experience of depth, distance, and even the passage of time would be perfectly consistent and real to us, just as a character in a holographic projection experiences its world as fully 3D. The truth of its existence, however, would be rooted in that 2D surface. Consider the profound implications of this. Our search for a theory of everything often focuses on unifying gravity with quantum mechanics in 3D space-time. But if our universe is holographic, then the underlying theory might be simpler, operating on a 2D surface, and our 3D physics would be a much more complex manifestation of that simpler, more fundamental reality. It could be that the very laws of physics we have painstakingly uncovered are the emergent rules of a holographic projection. This is not to diminish our existence, our consciousness, or the beauty of the cosmos. Quite the opposite. It imbues reality with an even deeper layer of mystery and elegance. It suggests that the universe, in its infinite wisdom, has found an incredibly efficient way to store and process information, creating worlds within worlds, dimensions within dimensions. Our room with no windows is not merely a contained space, but a masterpiece of cosmic engineering, a holographic projection of an even grander design. The awe and wonder this evokes are immense. It transforms our understanding of reality from a straightforward, tangible experience into a multi-layered, almost mystical dance of information and emergence. We are living, breathing beings, experiencing a universe that is, to us, undeniably real, yet whose deepest truth might be an elegant, boundary-encoded secret. So, as you gaze up at the night sky, at the countless stars and galaxies, consider this. What if every single star, every planet, every atom, every thought you've ever had is part of a magnificent cosmic hologram? If our universe is a black hole, physically contained and perhaps holographically projected, then what other fundamental aspects of our perceived reality are shaped not by an isolated, self-sufficient cosmos, but by the echoes and whispers of a grander, unseen dimension? If this journey through cosmic enigmas has sparked your curiosity and expanded your mind, then join us on future explorations. Subscribe to Celestial Enigmas for more profound insights into the universe and our place within it. Thank you for being a part of this incredible adventure.